Welcome to Pomodoro Joe for Friday, March 10th, 2023. Today we're doing LeetCode problem 382, linked list random node. This is a medium problem. Given a singly linked list, return a random node's value from the linked list. Each node must have the same probability of being chosen. Implement the solution class. Solution list node head initializes the object, blah, blah, blah. Int get random chooses a node randomly and returns its value. Okay, so let's take a look at our constraints. All right, so the constraints say we have between 1 and 10 to the 4th nodes. And their values range between negative 10 to the 4th and 10 to the 4th. And at most 10 to the 4th calls will be made. All right, and there is a follow-up, but we'll come back to that. All right, so with that, we'll put 25 minutes on the Pomodoro timer and get started. So I think because we have such a limited number of nodes in our list, between 1 and 10 to the 4th, let's just keep an array of the nodes, and then we can randomly index into the array when we call getRandom. That'll be pretty straightforward. So let's see. So we'll just have a list of nodes, and we'll have to start at node. Okay, so in the init, we're going to create a list, a member variable list called nodes, and then we'll just go through all of the nodes in our list, and we'll just add each node to our list of nodes. All right? And then when we get random, let's see, we'll have to generate some random index. So one way to do that is just use the random library, and let's see, I think it's called randint, and you pass it a range. So we can go from 0 to, I guess, the length of our nodes. -1. I think it's inclusive and we don't want to go outside of the bounds. All right, and then we can just return self nodes at that index, and we have to return the value. Oh, interesting. So we're returning the value, which gives me an idea for some optimization, but let's just see if this works first. I don't know why I had a semicolon there. Try that again. All right, that works. Let's see if we can pass all the runtime tests. And we do. So that's pretty straightforward. We beat 79% for runtime and 15% for memory, so not terrible. So what can we do to optimize this? Well, one thing I already noticed is we're just returning the value of the node, which means we don't have to store the node itself. We can just store the node's value, and then we can return the value at the index. The other thing, we're calling this length multiple times, so let's just cache that out here. So once we've calculated our list, we can have some node count. All right, and then we can just reference that instead of calculating the length each time. Okay, so 2 small optimizations. Let's see if that makes any difference. That actually makes things worse. That's surprising. We do better with memory, being 73%, but we're down to 51% for runtime. That is surprising. Let's do one last thing here. I guess maybe pulling the value out is more expensive than just storing the node and only pulling it out when you need it. So let's go back to storing the node. And then we'll return .val here. And instead of having some index, we'll just pass this whole thing in. All right, let's see if that helps. Not really. Interesting. So I wonder if it wasn't that we were storing the value, it was more this length calculation. Let's go back and not do our length calculation here. That would be shocking to me if that's the case. $76, and that compares to 79. So it doesn't really save us anything to store the value instead of the node. All right. So this is one way to do it. I guess one last thing I will try is we can use a set instead of a list. Now if we use a set, then we'll have to do an add here. And instead of adding the value, we will have to add the node, because if you add the value, it will basically get rid of redundancy, which means that the probabilities will be all thrown off. So we have to keep the node and not use the value. Okay, and then in here we can't use this random int, so we'll have to do something more like, let's see, what is that? I think it's random selection. Is that right? And then we pass in our nodes. And I think we pass in how many we want. And then I think that will give us back, let's see. This might be totally wrong, but I think that will give us back a list of nodes that are randomly selected, but we'll get a list of 1. Let's see if that's right. I could be totally wrong on this. Yeah, that's not right. Let's do a quick search here. It's not random selection, it's random sample. Okay, let's try that again with random sample. Okay, let's see if that's any faster. I doubt it, but you never know. Not even close, 24%. Okay, so now we know a couple different ways to go about doing this. Let's jump down to this special follow-up here. So follow-up, what if the linked list is extremely large and its length is unknown to you? Could you solve this efficiently without using extra space? So right now we're storing this set or list of all the nodes. This is saying, can we do this without having any extra space? So let's do that. I can't imagine it's going to be any more efficient, but you never know. So for this one, we will basically keep a current node. We'll just keep a node that we're currently at. Then we will generate random offsets from that node. And we'll need to basically start that node at some random offset to begin with. We don't want to start it at the head. We do, however, need to keep the head around, just in case we go off the end of the list, we'll have to wrap around to the head of the list again. Okay, so for now we'll start the self node at head, but then we need to create a random offset. So let's do that. And again, we can do random.randInt, and we'll go from 0 to, let's see, we don't know how long the list is, but it tells us the max is 10 to the 4th. So 10 to the 4th. All right. Now we need to offset our current node by some random offset. So let's see. To do that, we'll keep a track of a count. I wonder if it's faster to keep track of a count or to use a range. Let's use a range. And we, of course, have to make sure if we go off the end, we wrap around to the beginning. Okay, so now we've generated some random offset. So on the initializer, we have some random node. Then in here, we'll do an additional offset. Let's do that here. Okay, so now this should be definitely random. Okay, now I'm concerned this won't run in the time that we need it to, but there are things that we can do to fix that. Let's see, what did I do wrong? I have a typo. Try that again. Okay, so this works, but will it run in the time that we need? Probably not, considering we're going through 10,000 links every time. Oh, it does. It runs, but very poorly. We only beat 5.2 for runtime. We beat 73% for memory. So it works. It's just not a very great algorithm. So a couple things we can do to optimize this. We could drop this down. I don't know how far we can drop this down. So let's just drop it down to say 1,000. Let's see if we can just do some random offset from here. So that still works. What if we drop it down to 100? Will that still work? Well, let's submit this and see if 100 gives us enough variation for this to work properly. It still works. And now we're beating 97% for memory, but only 16% for runtime. So the 97% for memory makes sense because we have very little memory overhead. We're just storing 2 pointers here. The runtime, however, because we're going through 10,000 different nodes to begin with, it's going to be slow. We could maybe optimize this. If we keep track of the count, when we get to the end here, we're wrapping around, then we know exactly how many nodes are in this list. So instead of taking the worst case list, we can take the actual list count. Yeah. Let's see, should we try that? I'm like hesitant to try that. All right, we'll try it. Why not? Sure. All right. So now if we wrap around, we're actually going to break out of here. We will need to do another randomized list because clearly at this point we're back to the head. So we need to do another random offset, but this time our random offset can be more focused. Let's see, actually we'll do it inside here. So we only do it if we reach the end of the list. Yeah, I think that makes sense. This is pretty ugly. Okay, so we'll create a new random offset, but this time it'll be up to our self.count. All right, let's see here. This is super ugly. Okay, and now down here in this offset, we can basically focus our offset a little bit better. Let's try that. Now this may not work. Let's see. All right, it still works. We're beating 40% for runtime, 35% for memory. Not bad, not great, but not bad. So one thing I've noticed, like we have the same code here and here. What if we replace this with just a call to get random? We can ignore what it returns. So let's just try that. All right, let's see if that still works. It works. We do worse on our runtime. We do a little bit better on memory. It's a trade-off. Okay, we didn't get a 90% on this one. I'm a little bit annoyed by that, but you know what? It's all right. We did a bunch of submissions. We got a bunch of practice on linked lists. We got some information on getting random elements. So yeah, this one's a win. We learned a lot. Okay, hope you enjoyed this. Hope you had fun. I encourage you to try this one. Again, this is LeetCode problem 382. Try it on your own. See if you can get that 90%. All right, that's it for me. Hope you had fun. Hope you enjoyed this. Hope you learned something. And I hope you write better code.